Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to lecture 34 of the course Marine Renewable Energy Systems Analysis, Design and Development. I am Dr. Basangoda I. Patil, Assistant Professor in the Department of Civil Engineering, PDEU, Gandhinagar. This lecture is on TSUSUCA Dolphin, its reliability assessment, FMEA and maintenance analysis. In the previous lectures, we discussed the conceptual development of TSUSUCA Dolphin, its hydrodynamic behavior, numerical investigations and experimental studies under both regular and irregular wave conditions. We observed that the platform is capable of effectively harvesting wave energy while maintaining favorable dynamic characteristics. However, successful development of any offshore renewable energy system requires more than good hydrodynamic performance and high energy conversion efficiency. The system must also operate reliably over long periods in harsh environment. Offshore structures are continuously exposed to cyclic waves, leading fatigue loading, corrosion, wear and environmental degradation. These factors can significantly influence operational life, maintenance requirements, and overall economic viability. Therefore, in this lecture, we shift our focus from performance evaluation to reliability engineering. We will begin by introducing the fundamentals of failure mode and effects analysis, which is commonly known as FMEA, which is a systematic technique used to identify potential failures during the design stage itself. The objective is to anticipate failures before they occur, evaluate their consequences, and develop mitigation strategies. Next, we will discuss maintenance and risk assessment, which will help engineers determine which components require frequent inspection, preventive maintenance, and or design improvement. So, finally, we will examine how Monte Carlo based reliability evaluation combined with the probabilistic approaches such as variable reliability analysis can be used to estimate failure probabilities and maintenance intervals for different components of SUSUCA Dolphin and its power takeoff systems. By the end of this lecture, you will understand how reliability assessment can be integrated with engineering design to develop offshore wave energy converters that are not only efficient but also robust, maintainable, and economically sustainable throughout their service life. Let us begin by understanding why reliability assessment is needed, particularly which is important for offshore wave energy systems. Before discussing failure mode effect analysis, it is important to understand why the reliability assessment is essential. Unlike many land based renewable energy technologies, wave energy converters operate in one of the most challenging engineering environments. Offshore structures are continuously exposed to waves, currents, wind, corrosion, and changing environmental conditions throughout their service life. One of the primary challenges is a continuous cyclic wave loading. Every passing wave induces motion and load fluctuations in the structure and its power takeoff system. Over thousands and even millions of loading cycles, these repeated stresses can lead to fatigue damage in structural and mechanical components. Another major concern here is corrosion and material degradation. The marine environment contains salt water, moisture, and biological activity that can accelerate deterioration of metallic components, bearings, joints, shafts, connectors, and electrical systems are particularly vulnerable if adequate protection and maintenance are not provided. A further challenge is that maintenance across offshore is often difficult and expensive. Unlike laboratory equipment or land based machines, offshore devices may require specialized vessels, trained personnel, and favorable weather conditions for inspection and repair. Even a relatively minor failure can result in significant downtime and economic losses. So, this directly affects the life cycle cost of the system. While energy conversion efficiency is important, the overall success of a wave energy converter depends equally on how reliably it can operate over a long periods with minimal maintenance interruptions. Therefore, when designing offshore systems such as SUSUCA Dolphin, engineers must ask a very important question: can the system survive long-term offshore operation while maintaining acceptable performance, reliability, and maintenance requirements? Answering this question requires systematic reliability assessment methods. One of the most widely used approaches for this purpose is failure mode and effects analysis, or FMEA, which helps engineers identify potential failures before deployment and development strategies to reduce their impact. Let us now examine the reliability challenges encountered in the offshore wave energy converters in greater detail. Having understood why reliability assessment is necessary, let us now examine the specific challenges faced by wave energy converters during offshore operation. Unlike conventional mechanical systems operating in controlled environments, wave energy converters function continuously in the ocean, where they are exposed to dynamic loads and aggressive environmental conditions throughout their service life. The first challenge is mechanical wear. Many wave energy converters contain moving components such as bearings, pins, shafts, connecting rods, hinges, and power takeoff mechanisms. Continuous oscillatory motion caused by waves results in friction and gradual wear of these components. Over time, wear can reduce efficiency and eventually lead to failure. The second challenge is corrosion. Salt water is highly corrosive to metallic structures and mechanical equipment. Even with protective coatings and corrosion resistant materials, long-term exposure to the marine environment can degrade structural and mechanical components. Corrosion not only weakens the material but can also accelerate fatigue crack growth. A third major concern is bearing failure. Bearings are often used in rotating and oscillating components of PTO systems because they experience repeated loading and motion cycles. Bearing wear and fatigue are among the most common failure mechanisms in offshore machinery. Another important reliability issue is electrical faults. Generators, electrical coils, cables, insulation systems, sensors, and power conditioning units may suffer from insulation degradation, moisture ingress, short circuits, or connection failures. Such failures directly affect the power generation capability. We must also consider structural fatigue. Offshore structures experience millions of load cycles over their design life. Even when stresses remain below the ultimate strength of the material, repeated loading can eventually initiate cracks and lead to fatigue failure if not properly addressed during design. Finally, offshore devices must survive extreme wave events. Storm waves, rogue waves, and severe environmental condition can impose loads significantly greater than those encountered during normal operation. Therefore, reliability assessment must consider not only average operating conditions but also extreme scenarios. All these failure mechanisms have important consequences. First, they can lead to reduced power generation, resulting in lower energy output and reduced economic return. Second, failures cause increased downtime, meaning the device remains non-operational until repairs are completed. Third, offshore repairs often require vessels, equipment, and skilled personnel, leading to higher maintenance cost. Therefore, reliability assessment is not merely a safety exercise, it directly influences energy production operational availability and overall project economics. To systematically identify and prioritize these potential failures before deployment, engineers commonly use a powerful tool known as failure mode and effects analysis or FMEA, which we will discuss next. Now that we have discussed the reliability challenges associated with offshore wave energy converters, let us introduce one of the most widely used reliability assessment tools in engineering practice, namely failure mode effect analysis or FMEA. FMEA is a structured and proactive methodology used to identify potential failures before they occur. The fundamental philosophy behind FMEA is simple. Rather than reacting to failures after deployment, engineers attempt to anticipate failures during the design stage itself. The primary objectives of FMEA are to identify, prioritize and limit potential failures. By systematically examining each component and its possible failure modes, engineers can determine which part of the system require design improvements, enhanced monitoring or even more frequent maintenance. The figure shown on this slide highlights the importance of early failure mode identification. Let us now first look at the figure on the left side, which represents the late failure mode discovery. In this case, the failure mechanism is identified only during the testing, launch or even operational stages. As a result, the significant amount of time is required to develop corrective actions. More importantly, the cost associated with implementing those corrective measures increase substantially. Design modifications become difficult, testing may need to be repeated and operational delays can occur. Now consider the figure on the right side, which represents early failure discovery. Here potential failures are identified during the definition, characteristics and development stages. Because the problem is recognized much earlier, corrective actions can be implemented quickly and economically. The development time is reduced and the overall cost of the mitigation remains significantly lower. The time is reduced here and overall cost of the maintenance is also minimized. This is one of the major reasons why FMEA has become a standard practice in industries such as aerospace, automotive engineering, offshore structures, nuclear systems and renewable energy technologies. For offshore wave energy converters such as TSUSUCA Dolphin, the importance of FMEA is even greater. Offshore maintenance is expensive, weather dependent and often logically challenging. Therefore, identifying vulnerable components before deployment can substantially improve reliability and reduce life cycle costs. It is important to note that FMEA is not simply a failure prediction tool, rather it is a decision making framework that helps engineer answer questions such as which component is most critical, which failure mode has the highest impact, which failure require immediate design attention and where should maintenance resources be focused. In the next slide, we will see how FMEA is implemented in practice through a systematic step-by-step procedure. Having understood the importance of FMEA, let us now examine the systematic procedure used to perform a failure mode effect analysis. One of the strengths of FMEA is that it follows a logical and structured workflow. This ensures that every component of the system is evaluated consistently and no critical failure mode is overlooked. The first stage is system definition. At this stage, the boundaries and objectives of the system are clearly established. For our study, the system under consideration is the SUSUCA Dolphin platform together with its various power takeoff mechanisms and associated components. The second step is component identification. Here the entire system is broken down into individual components and subsystems. Examples include dolphin buoy, connecting rods, bearings, hinges, generators, structural members, hydraulic components and electrical systems. Since failures occur at the component level, identifying these elements is a critical step. The third step is failure mode identification. For each component, we ask a simple question: how can this component fail? For example, a bearing may wear out, a structural member may experience fatigue cracking, a generator may develop insulation failure, or a connecting rod may buckle under repeated loading. Once potential failure modes are identified, we proceed to severity assessment. Severity evaluates the consequences of a failure. Some failures may only cause minor reduction in performance, while others may completely stop power generation or compromise structural integrity. The next is occurrence assessment. Here we estimate how likely a particular failure is to occur during the operational life of the system, and components subjected to repeated cyclic loading generally have a higher probability of failure compared to lightly loaded components. After that comes detection assessment. This evaluates how easily a failure can be identified before it causes serious consequences. Failures that are difficult to detect generally pose greater risk because they may remain unnoticed for long periods. Using the severity, occurrences and detection ratings, we then perform the risk priority number or RPN calculation. This numerical value allows us to rank failure modes according to their risk level and identify which components require immediate action or attention. Finally, based on the RPN values, we develop a mitigation measures. These may include design modifications, improved material selection, protective coatings, enhanced inspection schedules, continuous monitoring systems, or preventive maintenance plans. Thus, FMEA provides a systematic pathway from failure identification to risk reduction, enabling engineers to improve reliability even before the system is deployed. In the next slide, we will look more closely at the three parameters used in FMEA: severity, occurrence, and detection, and understand how they are combined to quantify risk. After identifying potential failures, the next step in FMEA is to determine which failures are most critical and therefore require immediate attention. This is accomplished by using the risk priority number. commonly referred to as the RPN. The RPN is a numerical measure of risk and is calculated using three parameters: severity, occurrence, and detection. Let us briefly understand each of these parameters. The first parameter is severity, denoted by the letter S. Severity measures the seriousness of the consequences if a particular failure occurs. A value of 1 indicates minimal impact on system performance, whereas a value of 10 represents a catastrophic failure that could completely disable the system or create serious safety concerns. The second parameter is occurrence, represented by O. Occurrence reflects the likelihood of a failure happening during the operational life of the system. A rating of 1 indicates that a failure is highly unlikely, whereas a value of 10 suggests that failure is expected to occur frequently. The third parameter is detection, represented by D. Detection evaluates how easily a failure can be identified before it causes significant consequences. A value of 1 means that the failure is easy to detect through inspection or maintenance activities. A value of 10 indicates very difficult to detect and may remain unnoticed until it results in system malfunction. So, the risk priority number is then calculated as the multiplication, the product of severity, occurrence and detection. Since each parameter ranges from 1 to 10, the maximum possible RPN value is 1000. A higher RPN indicates a higher risk failure mode and therefore higher priority for corrective action, redesign, inspection or maintenance planning. The lower part of this slide shows a typical FMEA worksheet. For every component, we document the function or a process, possible failure modes, the resulting effects and likely causes of failure and existing control measures and recommended corrective actions. For example, consider the dolphin buoy whose primary function is to provide heave displacement and force required for energy extraction. If the body fails to generate the desired motion, the resulting effect is reduced or even a zero power generation. Based on the severity, occurrence and detection ratings assigned, the calculated RPN here is 168. These are the values: severity 6, occurrence 4 and detection 7. RPN is 168, indicating that it is one of the critical components requiring attention. Similarly, for LMEG, linear motion electricity generator, electrical faults such as cable failures or blocked piston motion can lead to complete loss of power output. The calculated RPN in this case is 98, suggesting a moderate but significant level of risk. Thus, RPN serves as a practical decision making tool that allows engineers to focus resources on the most critical failure modes rather than treating all failures equally. In the next slide, we will briefly review the rating scales and rating scales used for severity, occurrence and detection before applying FMEA. Having understood the fundamentals of FMEA and risk prioritization, we are now ready to apply these concepts to the various power takeoff systems investigated for SUSUCA dolphin. As discussed in earlier lectures, the power takeoff or PTO system is the most critical subsystem of any wave energy converter because it is responsible for converting wave induced motion into useful electrical energy. At the same time, it contains several moving and interacting components, making it one of the most vulnerable parts from a reliability perspective. The figure on this slide presents 4 PTO concepts considered in this study. The first is LMEG. In this configuration, the reciprocating motion generated by the wave induced movement of SUSUCA dolphin directly drives a linear generator. The major components include magnets, coils, moving rods, guide mechanisms, electrical windings and support structures. Potential failure modes include coil insulation breakdown, magnetic rod failure, rod misalignment, corrosion and electrical faults. The second PTO concept is slider crank mechanism. Here the linear motion of the dolphin buoy is converted into rotational motion through a connecting rod, a crank, pin and a crank wheel. Critical components include the connecting rod, crankshaft, bearings, pins and rotating wheel. These components are subjected to repeated cyclic loading and therefore may experience wear, fatigue, buckling or misalignment. The third concept is the Scotch oak mechanism, which converts reciprocating motion into rotary motion using a pin and a slot arrangement. While this mechanism is relatively simple, the sliding contact between the yoke and pin introduces additional wear and maintenance concerns. Typical failure modes include yoke wear, pin fracture, bearing degradation and fatigue damage. Finally, the toggle mechanism utilizes a linkage arrangement consisting of connecting rods, links, crank elements and rotating wheels. This mechanism can amplify force and displacement, which may be advantageous for energy extraction. However, the additional joints and links increase the mechanical complexity and introduce more potential failure location. An important observation is that all 4 PTO systems contain multiple moving components exposed to wave induced cyclic loading throughout their operational life. Therefore, even if 2 systems exhibit similar energy conversion performance, their reliability and maintenance requirements may be significantly different. This is precisely why reliability assessment becomes important. Our objective is not only to determine which PTO system produces the highest power, but also to identify which system can operate for the longest duration with the least maintenance and lowest risk of failure. In the following slides, we will see how each PTO systems in detail and identify the critical components that will be evaluated using FMEA, viable reliability analysis and Monte Carlo simulation. Now, let us look at the FMEA results of the SUSUCA Dolphin platform along with LMEG. Since the complete FMEA table is quite detailed, I will focus only on the key findings that are most relevant from a reliability perspective. The analysis considered all major components involved in energy capture, motion transmission, power generation and energy storage. These include dolphin body, pivot assembly, bearings, LMEG, floats, battery bank and electric generator. Among all these components, the dolphin buoy was identified as the most critical component, which with the highest risk priority number 168. This result is quite intuitive because the dolphin buoy is directly responsible for capturing wave energy and generating the heave motion required for power extraction. If the buoy fails to operate, sufficient displacement or force, the entire energy conversion process is affected, leading to little or no power generation. The second important component is the float system, which has an RPM of 112. The floats provide buoyancy and stability to the platform. Any instability or capsizing tendency can significantly affect the motion response and overall functionality of the system. The linear motion electric generator itself has an RPM of 98. The primary failure modes identified include piston blockage, and cable faults and electrical issues with the generator. Since the LMEG is responsible for converting mechanical motion into electrical energy, failures in this component directly impact power output. The pivot assembly, which transfers the motion through rotational movement about the hinge, also exhibits a relatively higher RPM value of 96, where friction and manufacturing defects are the primary concerns in this case. Okay, the bearings shows a moderate RPM value of 75. Bearing failures generally lead to increased friction, reduced efficiency and eventual deterioration of the system performance. In contrast, the components such as the battery bank and electrical power generator exhibits relatively lower RPM values, indicating comparatively lower risk levels within the overall systems. An important outcome of this analysis is that highest risk components are primarily associated with the wave energy capture and motion transmission rather than energy storage. This observation highlights the importance of robust mechanical design and careful material selection and adequate testing of offshore wave energy systems. The recommended mitigation measures include improved buoy design, enhanced lubrication, better inspection procedures, use of high quality electrical components and extensive laboratory and wave basin testing before deployment. So, FMEA has helped us identify which components deserve the greatest attention during design and maintenance planning. However, FMEA only tells us which components are critical. It does not tell us how failures evolve over time. For that, we need reliability analysis and maintenance modeling. which we will discuss next. Up to this point, we have identified the critical components and failure modes using FMEA. However, FMEA alone does not tell us when failures are likely to occur or how frequently maintenance may be required. To answer those questions, we need a reliability modeling framework. The methodology adopted in this study is shown here. The process begins with FMEA, where the critical components and dominant failure modes are identified. Once the important failure mechanisms are known, reliability models can be developed to evaluate their behavior over the time. The next step involves the Weibull distribution, which is one of the most widely used statistical distributions in reliability engineering. It is particularly suitable for modeling fatigue failures, wear related degradation, corrosion effects, and long term deterioration of mechanical components. The Weibull cumulative failure function shown here represents the probability that a component has failed by a given time. The model contains two important parameters. The first parameter is beta, known as the shape parameter. It controls how the failure rate changes with time. The second parameter is eta, denoted by this symbol eta, and called as characteristic life. It represents a characteristic operating duration associated with component survival and failure behavior. In offshore engineering, applications are Weibull distributions are extensively used for modeling fatigue damage in structures, bearing wear corrosion related degradation, and equipment reliability. Once the Weibull parameters are established for each failure mode, we proceed to Monte Carlo simulation. The primary purpose of Monte Carlo simulation is to account for uncertainty. In reality, failures do not occur at exactly the same time for every component. Material properties vary, loading conditions fluctuate, manufacturing tolerances differ, and environmental conditions change continuously. Therefore, instead of using a single deterministic value, Monte Carlo simulation generates thousands of random realizations of component behavior. These repeated simulations provide a probabilistic representation of system performance and failure occurrence. Using this approach, we can eliminate failure probability as a function of time. Reliability degradation over the service life and expected maintenance intervals and overall operational behavior under uncertainty conditions. Finally, the resulting failure probabilities are used to develop maintenance strategies and estimate the mean time to maintenance or MTTM for different components. In simple terms, FMEA identifies what can fail. The Weibull model describes how failures evolve with time, and Monte Carlo simulation quantifies the uncertainty associated with those failures. Together, these tools provide a comprehensive reliability assessment framework for offshore wave energy systems. Let us now apply this framework to SUSUCA dolphin and study how the probability of failure and maintenance requirements evolve over time. Having identified the critical components through FMEA, and establish the reliability modeling framework. Let us now examine the actual reliability results for the SUSUCA Dolphin platform equipped with linear motion electricity generator. This slide represents two important outputs of the reliability analysis. The figure on the left shows the failure probability evaluation with the time, while the figure on the right side presents the corresponding mean time to maintenance or MTTM for different failure modes. Let us first focus on the failure probability curves. The horizontal axis represents the operational time in hours, extending up to 10,000 hours, while the vertical axis represents the cumulative failure probability or probability of failure. Each curve represents or corresponds to a specific failure mode identified through FMEA. These include the primary structure fatigue, hinge wear, float fatigue, magnetic rod fatigue, coil insulation breakdown, rod misalignment, corrosion damage, and buoyancy loss. A key observation is that all failure probabilities increase progressively with operating time. This behavior is expected because fatigue, wear, corrosion, and material degradation accumulate continuously during service. However, the rate of increase differs from one failure mode to another. Some components deteriorate faster and therefore require earlier maintenance intervention. Now, let us look at the mean time to maintenance results shown on the right. The lowest mean time to maintenance is associated with magnetic rod fatigue, approximately about 4,104 hours. This indicates that magnetic rod assembly is one of the most maintenance sensitive components in the LMAG system and may require more frequent inspection or replacement. The next critical failure mode is the primary structure fatigue. With an MTTM of approximately 4,446 hours, since the primary structure continuously experiences wave induced cyclic loading, fatigue damage becomes an important consideration in long term offshore deployment. Similarly, coil insulation breakdown exhibits a mean time to maintenance of approximately 4,841 hours. This highlights the importance of protecting electrical components from moisture ingress, thermal effects, and environmental degradation. On the other hand, corrosion damage shows the highest MTTM, approximately 6,861 hours, indicating comparatively slower degradation under the assumed reliability parameters. Another important observation is that as service life increases, the failure probability of all components gradually approaches unity. In other words, if a component operates for a sufficiently long duration without maintenance, failure eventually becomes highly likely. Therefore, these results provide valuable information for maintenance planning rather than waiting for failures to occur. Operators can schedule inspections and preventive maintenance based on the expected maintenance intervals of critical components. In summary, the reliability analysis identifies magnetic rod fatigue, structural fatigue, and coil insulation degradation as the dominant maintenance drivers for the SUSUCA Dolphin platform equipped with the LMEG system. We will now perform a similar analysis for another PTO concept and compare how reliability characteristics change with the choice of power takeoff mechanism. Let us now examine the reliability failure behavior of the slider crank PTO. The figure on the left side shows the evaluation of failure probability with the operating time, and the right side figure indicates the mean time to maintenance for key components of slider crank PTO. Among the various failure modes, crankshaft fatigue has lowest critical is the most critical and has the lowest MTTM, approximately 3,586 hours. This indicates that crankshaft is subjected to significant cyclic loading and therefore requires close monitoring during operation. The next important maintenance related failure mode is bearing wear. With an MTTM of approximately 4,461 hours. Since bearings are continuously involved in rotational motion transfer, wear is expected over long service periods. The connecting rod buckling failure mode shows an MTTM of about 5,336 hours, while the corrosion damage also exhibits comparatively higher maintenance interval of around 5,868 hours. Increasingly, pin fracture has the highest MTTM, approximately 7,099 hours, indicating that it is among the least critical failure modes within this PTO configuration. Overall, the failure probability curves increase gradually with the time, reflecting the cumulative effects of fatigue, wear and environmental degradation. However, compared to several other PTO concepts, the slider crank mechanism demonstrates relatively balanced reliability characteristics and longer maintenance intervals for many of its components. These results suggest that although crankshaft fatigue remains a key design concern, the slider crank PTO exhibits favorable reliability performance for long-term offshore operation. In this slide, we'll see we'll continue the reliability assessment for the remaining PTO mechanisms and compare their maintenance requirements with those of slider crank system. After evaluating the individual PTO concepts, we can now compare their overall reliability characteristics and maintenance requirements. This table here summarizes the major findings from the FMEA reliability assessment and maintenance analysis of the 3 PTO. Let us begin with slider crank mechanism. The slider crank system benefits from a proven design and relatively balanced performance. The primary failure modes include characteristic crankshaft fatigue, bearing wear, pin fracture, joint failure, platform fatigue and corrosion damage. Its mean corrosion damage, its mean time to maintenance ranges from approximately 4,461 to 7,098, or nearly 7,100 hours, which is the highest among the mechanisms studied. As a result, it demonstrates the best long-term reliability and is particularly attractive for offshore applications where maintenance access is limited. The second mechanism is the Scotch hook mechanism. In its main advantage is smooth sinusoidal motion with fewer linkages. However, yoke, pin and bearing components are subjected to continuous contact and wear. The MTTM ranges approximately from 401.2 to 7025 hours, indicating moderate reliability. While it can provide efficient motion conversion, it requires careful alignment and regular inspection. The third configuration is the toggle mechanism. The major advantage of this system is displacement amplification, which can be useful when larger motion transfer is required. However, the presence of additional links and joints introduce more potential failure locations, failure modes such as connecting rod failure, crankshaft wear, hinge loosening, pin shear failure, link fatigue, rotating wheel imbalance are the different critical failure modes. The MTTM ranges between approximately 4333 to 6203 hours, resulting in comparatively lower reliability than the slider crank system. Overall, an important conclusion emerges from this comparative study. Although all three mechanisms are capable of converting wave induced motion into useful power, their reliability characteristics differ significantly from a long term offshore operation perspective. The slider crank mechanism provides the most favorable balance between performance, reliability, structural robustness and maintenance requirements. This observation highlights an important engineering principle that most suitable PTO system is not necessarily the one that produces the highest instantaneous power, but rather than one that can deliver reliable performance over many years with manageable maintenance requirements. Let us now conclude this lecture by summarizing the major findings obtained from the reliability, FMEA and maintenance analysis of SUSUCA dolphin. Let us conclude this lecture with these key findings and key takeaways. The first important takeaway is that reliability is a fundamental requirement for the successful deployment of offshore wave energy converters. High energy conversion efficiency alone is not sufficient. A system must also operate safely, reliably and economically throughout its service life. Second, we saw that failure mode effect analysis, FMEA, provides a systematic framework for identifying and prioritizing critical failure modes during the design stage itself by identifying vulnerable components early. Engineers can implement corrective actions before deployment and thereby reducing the risk and life cycle cost at the design stage itself. Third, the combination of viable reliability analysis and the Monte Carlo simulation provides realistic estimates of failure probability and then mean time to maintenance for key components. These tools help engineers move beyond deterministic design and account for uncertainties associated with the real offshore environments. The analysis also demonstrated the significant influence of fatigue, wear, corrosion, structural degradation and electrical failures on the long-term performance of offshore energy systems. These failure mechanisms must be carefully considered during the design, operation and maintenance planning. Finally, the study highlighted the successful offshore renewable energy system require an integrated approach, which where performance, reliability, maintainability and life cycle economics are considered together. Such an approach leads to more robust, sustainable and commercially viable wave energy technologies. In summary, reliability engineering is not an additional design activity. It is an integral part of the engineering design process that ultimately determines whether a promising concept can successfully transition from the laboratory to long-term offshore deployment. With this, we conclude our discussion on SUSUCA dolphin reliability. assessment, FMEA and maintenance analysis. These are the key references used for this analysis. Thank you for your attention. Thank you.